Morning everyone, my name is Singhao, and I'm accompanied by Boyan, my teammate. We will be talking about our spacecraft, HS-1 Odyssey. We are a group from Naho High School, consisting of Boyan, Darius, Junsi, Yangzuo, and I. So, what are our goals as HS-1 Odyssey? We seek for a foolproof plan for space mining, which includes our goals, sampling rocks from foreign asteroids, assisting in material discovery, and ensuring ample resources for mankind in the coming era. Space mining missions are no special feat, so please support us and our missions. This is our table of contents. We'll be starting off with space mining overview, then pre-mission analysis. Afterwards, my teammate Boyan will take over to explain our design plan, financial plan, operation plan, and test analysis. Our team strive to reach for the stars and beyond, and retrieve what is needed to serve humanity better. Firstly, space mining overview. We have conducted an in-depth research on how space mining works, and have studied different aspects of space mining. The process of space mining is quite simple to understand. Man-made machines are sent out to space, they collect samples of asteroids, and they are brought back to humans where they are analyzed. However, there are still some drawbacks to space mining. Firstly, technological challenges. Developing advanced technologies for space mining poses significant technical hurdles, but with artificial intelligence becoming more and more advanced each day, this challenge is sure to not affect our mission with coming time. Secondly, high initial costs. Development of space mining technology requires substantial funding, but with the promise of valuable rocks on one end, we are sure to achieve these fundings. Lastly, political concerns. Space mining may lead to geopolitical tensions over resource ownership and control. As of now, space is still a public domain which can be used by anyone. Thus, this concern is not a problem. As of now, we are successful with our state-of-the-art technology. We are currently researching on workarounds for this topic and have seen much success in our planning and testing phases, which have allowed us to bring out prototypes that excel and are excellent candidates for space mining. Next, I will talk about our pre-mission analysis, where I will share with you our mission planning and managing our roadblocks. Firstly, cosmic radiation. Cosmic radiation could damage instruments and cause unreliable identification of material. It can also interfere with our electromagnetic signals and create noise and unreliability in the waveform we receive. Secondly, location. The surface of interest may be rocky, which may make it difficult to sample rocks without causing damage to the spacecraft. If the terrain is way too rocky, it can also affect the light tracing abilities of the spacecraft. Lastly, limited reach. Our spacecraft may not be in a good position or have a good approach to identify and collect material samples due to limited fuel and other resources. Next, I will talk about the system requirements. These are a list of systems aboard spacecraft HS-1 Odyssey. We have conducted multiple tests and simulations to ensure that our spacecraft is of top quality. Material tests. Materials are tested under multiple tolerance tests to ensure that they are suitable on our spacecraft. Mining tests. Space mining tools are put in simulated space environment to test for their suitability. AI tests. Artificial intelligence computers are trained to learn procedures and communicate with ground crew members and give commands. Instrument tests. Scientific instruments are tested to ensure their functionalities against elements. Thrust tests. Landing and takeoff systems are tested for aerodynamic hull design as well as thrust systems in order for maximum efficiency and conserve fuel. Adaptability tests. The rover ability to move about on foreign location is tested and given conditions such as sandstorms to adapt to. We have spent a long time dedicating our lives to the success of HS-1 Odyssey. Theoretical technology will not work in our mission, and we are fully aware of their limitations. However, we promise to make full use of what we have learned to make this mission successful. Next, I'll hand the time to my teammate Boyan, who will share with you the rest of our content.
Now, we'll be talking about the design of the HS-1 Odyssey spacecraft. There are 6 main parts to the design of the spacecraft: the mining, thrust, power, navigation, hull, and movement components. All of these 6 components come hand in hand in order to create an ideal spacecraft that is capable of successful space mining. This is a rough outlook and blueprint of what our design will look like. Firstly, we have the mining component. We took a unique approach after doing a lot of research on the topic, and we've came up with a mining tool that is comprised of a fast rotating metal lock paired with a braking mechanism that has a sharp set of hard teeth that are rotating along with the lock. This allows the lock to break apart rock pieces into smaller pieces whenever it comes into contact. After the rocks are broken into smaller pieces, they're shoveled onto the collector shovel, which has 2 rotors. The rotors then push the small rocks up to the collector funnel, and this whole component is called the sample collector, and it allows the sample rocks to be collected into the spacecraft. Next, we have a suspension system on our mining tool, which allows the mining tool to move up and down while mining, thus allowing for dynamic mining. Last but not least, we have a scouting system comprising of a jet-powered scouting drone that scouts the area, feeding information back to the mining system, telling the mining system where to mine, as well as alerting the mining system of any dangers along the way. Next, we have our thrust design. Our spacecraft consists of mainly 1 active engine, 2 idle engines, and 1 auxiliary power unit to provide power to all the systems on board. The main active engine uses hydrogen and oxygen combustion, internal combustion, to give out thrust and provide a huge amount of thrust to the spacecraft, while our 2 idle engines uses ionic thrust to provide additional thrust to the spacecraft. This allows the spacecraft to have a total combined thrust of 2,700 metric tons. Next, we'll be moving on to the power provisioning systems on board the spacecraft. There are 4 main types of power provisioning systems. Firstly, we have solar power, radioisotope power, neutrino power, and battery power. While all 4 systems provide power to the spacecraft, the main source of power comes from solar power and battery power. Now, we'll be talking about the navigation system. For this, we took a special approach to our navigation and we have made use of something that has never done before. In our vectoring system, we have implemented AI as the fundamental component of navigation for the spacecraft. With highly intelligent computers, we're able to instruct AI to make decisions and carry out commands on board the spacecraft for us. Although this has never been done before and definitely carries a lot of risk, we are sure that AI technology will be able to function just fine in space and be able to make the accurate decisions that are required due to the amount of training that we have given the AI. We have also given AI on board the full access to all systems and all sensors, allowing it to detect any discrepancies and avoid any dangers. Next, we'll be moving on to the hull design. There's one main difference between our current hull design and the past hull designs. Instead of using aluminium for the hull, we have decided to use carbon steel and a mixture of Kevlar and a hydrogen shield. So why did we use carbon steel? It is because carbon steel is more lightweight and durable as well as more temperature resistant than aluminium, and the Kevlar and hydrogen shield is proven to block out a huge amount of cosmic radiation, keeping the spacecraft instruments safe. Finally, we'll be talking about the movement design of our spacecraft HS-1 Odyssey. The 4 main parts of the movement design are strong wheels, high hull maneuverability, high quality suspension, and a gyroscopic balance. Next, we'll be moving on to the financial plan of the project. For the project, we have 3 main ways of pooling funds, with the main way being creating an IPO funding on Nasdaq to pool 40% of the funds. Our projected costs for the whole project are $4.8 billion for constructing the spacecraft, $330 million for launch services, and $970 million for research and testing. Next, we'll be going over the operation plan. First, in Phase A, we have our pre-mission analysis. In Phase B, we have our definition and planning. In Phase C and D, we have design and creation, which we are going through now. And in Phase E, we are going to commence our operations. Now, we'll be going over some test results to give you some insight on what research we have done. Firstly, on our research on radiation resistance, we found that hydrogen in a liquid form is the best at blocking galactic cosmic radiation as well as solar particle event radiation. Therefore, we chose to implement hydrogen in our shielding of our spacecraft against cosmic radiation. Secondly, in our experiment of carbon fiber against aluminium, we found that although carbon fiber is a way more expensive candidate than aluminium, it excels in many criteria that are important for the building of the spacecraft. For example, carbon fiber has really high heat resistance, which allows carbon fiber to stay strong against super high intense temperatures, while aluminium will simply just melt at temperatures above usually 660 degrees Celsius, depending on the situation. Furthermore, carbon fiber has much higher tensile strength than aluminium, allowing it to stay intact under super high tensile stress, among other types of complex tensor stresses. Finally, we tested the feasibility of neutrino power. Neutrino power as of now is definitely a viable solution to providing energy. However, it only provides a very tiny amount of energy when compared to other forms of energy such as solar energy, and therefore it seems a little less feasible as of now. However, we think that in space there are much higher doses of neutrino power, and during cosmic events, many neutrinos of higher energy are given off, which are able to be captured through resonance and probably provide a much higher amount of electrical energy to our appliances. And therefore, we think that, yes, neutrino power is in fact something that we could leverage off of in the future. All in all, that's it from the HS-1 Odyssey team, and we hope that we have gained your interest. Special thanks to NASA for the references to data and other research information. And with that, thank you.